LeetCode 736, Parse Lisp. Expression isn't just academic, it mirrors how compilers, interpreters, and config engines evaluate nested logic. Like dealing with layered templates or tangled settings files, it's not the parsing that's tricky. It's managing scope. We need to track variable lifetimes across deeply nested levels. So how do we avoid getting lost in the weeds and still build something clean and efficient? Let's waddle in with brute force. We'll handle this by using a single global scope to store variable values. It's not the most graceful solution, but it gets us moving. First, we drop in a global hash map. This acts as our scope, mapping variable names to their current values. To evaluate any expression, we create a main method that hands the real work off to a recursive parser. In that parser, our first check is whether we're looking at a plain value. If there's no outer parenthesis, it must be a number or variable. If it's a number, we pass and return it. If not, we treat it as a variable and fetch its value from our map. When we hit a full expression wrapped in parentheses, we peel off the outer shell to uncover the command and its pieces. Next comes tokenization. We split the stripped string into parts, handling nested expressions so each token stays intact. With our tokens ready, we grab the first one. That tells us which command we're about to handle. If it's AD, we evaluate the next two tokens recursively and return their sum. If it's mult, we do the same thing, but multiply instead. For a let command, we'll need to assign temporary variables. So first, we back up the current scope for safekeeping. Then we walk through the tokens in pairs, one variable, one expression, evaluating each and updating our scope along the way. Once all variables are assigned, we evaluate the final expression using our updated scope to get the result. To clean up, we restore the previous scope, making sure outer bindings aren't affected. And at the end, we hand back the value we got from evaluating the let block. To handle the token splitting, we build a helper that tracks open and closed parentheses, ensuring nested expressions stick together. This approach runs in big O of n squared, which adds up fast. For 1,000 characters, that's up to 1,000,000 operations. Space is big O of n for the recursion and the map. But watch out, since we're using a single global map, bad scoping or reusing variable names can break things. This isn't true lexical scoping, so it's fragile for deep nesting. The brute force method breaks down with real scoping rules. Let's improve it by modeling proper lexical scopes using variable stacks in a recursive parser. We kick things off by calling a recursive helper with the expression and an empty map to simulate scoped bindings. Inside that helper, if the expression is just a value, we check whether it's numeric. If it is, we return it straight away. If it's not a number, it must be a variable, so we look it up in our scope and grab the latest value from its stack. For expressions wrapped in parentheses, we strip the outer layer and pass the inside, using a smart tokenizer that respects nesting. The first token we pull tells us what we're dealing with, let, add, or mult. If it's add, we evaluate the two following tokens and return their sum. If it's mult, we evaluate both tokens and return the product. When it's a let expression, we evaluate assignments in order. So we create a new scope, cloning the current one to keep outer values safe. Then we walk through the variable expression pairs, evaluating each and pushing the result onto that variable stack in the new scope. Once bindings are done, we evaluate the final expression in this fresh scope and return its value. Our custom parser takes care of splitting the expression, tracking nesting so tokens don't get split mid-subtree. This version still runs in big O of n squared thanks to recursive calls and repeated parsing. But the space is also big O of n, And here's the big win. We simulate lexical scoping correctly using stacks. This mirrors how real interpreters handle block scopes and variable shadowing. And it's a favorite in FAANG interviews for good reason. We started with a brute force parser using one global scope, easy to grasp, but flawed in managing shadowed variables. Then we upgraded to a scoped recursive parser using stacks, a model much closer to how real compilers work. While both approaches have quadratic time, the scoped version adds precision, modularity, and correctness, a big deal in interview settings. Mastering this pattern shows you're not just parsing strings, you're thinking like a language designer. Try applying this to interpreters, expression trees, or template engines. Keep leveling up and keep paddling towards smarter solutions.